Hi. And I don't even present myself, but thank you. My name is Carlos Matallana. I'm from Protocol and Integration Team at Polygon Hermez, and I'm going to present the state tree that we are building in Polygon zkEVM. So, first of all, which is the goal of a state tree? So basically, the goal of the state tree is to save the persistent data across the history of a blockchain. In Ethereum is across all the blocks, and in the zkEVM it will be across all the batches. Also, the state tree, sound? Yes? Yes, like this, perfect. Okay, thank you. Also, the state tree needs to be deterministic. It means that when you add a set of data value into the state tree, the root should be always the same. Also, why do we use this kind of architecture? We use this kind of architecture in order to prove quite fast with a short amount of bytes that a certain data belongs to a root. In order to do this computation, it also needs to be fast. Also, regarding the zkEVM specifics, we need to use a hash function, okay, that is zk-friendly in order to compute it faster. And also, we need to care that the zkEVM state tree needs to be closest as the Ethereum one, because we want to mimic the Ethereum state tree. So, the first thing that I wanted to show is an overview of how it looks like the Ethereum state tree, okay? Maybe you are aware of how it is, but this is a very quick overview. The Ethereum state tree is a modified Patricia Merkle-Tree. It needs to be deterministic. It has 16 childs for each level, and the hash function that they use is the keycap hash function. There is the key when you insert some node in a Merkle-Tree. It has a key and a value. The key is the keycap of the Ethereum address, and the node in the Ethereum state tree is the keycap of the Ethereum account. And what are the fields inside the Ethereum account? It basically has the nonce, the balance, the storage root, and the code hash. I didn't put it here, but the code hash is the hash of the bytecode of a smart contract, and the storage root is another modified Patricia Merkle-Tree, which has all the storage key values that a smart contract has. Okay, so let's see an overview of the zkEVM state tree, okay? The zkEVM state tree is deterministic as well. It has 2 childs per level in the state tree. It's an sparse Merkle-Tree, meaning that when you compute the key, it also defines the path across the navigation through the state tree until it reaches the leaf. And the hash function that we use is the Poseidon hash function, which is a zk-friendly hash function. And what about the key and the value that we use in order to build the Merkle-Tree? The key is the Poseidon of the Ethereum address plus the leaf type. We will see in following the slide which kind of leaf types, but in the diagram, in fact, you have a spoiler. There are 4 different leaf types. And also the value that we're going to insert in the tree is 256 bits, basically, okay? So if you remember the previous slides, in Ethereum, you put all the data in the leaf, and here we split the data in different leaves. Okay, so let's go to the specification. First, I want to make it clear how the Poseidon input and output looks like, okay? The first thing to mention is that the Poseidon, it's a special hash function. We use a prime field, which is called Goldilocks. It's a short prime field. It could be encoded in 63.99 bits, okay? And the input of the Poseidon basically is an array of 8 elements, and each element is a field element, okay? And also it has another input, which is basically the capacity. It defines the hash function, the Poseidon itself, and its 4 field elements. And the output is 4 field elements. This is important when we will see how to make the different nodes and the leaves in the state tree. Okay, so in a Merkle-Tree, basically, which are the nodes that you can find in a state tree. This is a little bit generic, but obviously you can find the root, which is the summary of all the state tree. You can find the branch node, also known as a middle node. It has the left and the right child. The value is the left and the right child, hash it together. And also you can find the leaf node, which basically contains the value or probably the hash of the value. Also, I want to draw here the path, okay, which is this, and it defines the navigation across the state tree. This is very important, we will see why. Okay, so let's go to the specification itself. There is the branch node and the leaf node. So there is two kind of nodes, how to differentiate them. So here, the branch node, as I said previously, it contains the left child and the right child. So we put it all together. There are 8 field elements, and then we hash it all together. But here, the important thing is that we are hashing them using a capacity of 0,0,0,0, which is basically the hash function that we are using here. And it is very important, if you see the next slide, and this slide explains the leaf node, we are using a capacity of 1,0,0,0. This is basically a flag in order to differentiate a leaf node from a branch node. So you can see that you have either a branch node or a leaf node. Regarding the leaf node, what we want to insert in the leaf node is basically the final value. So we will take the value, we'll hash it. It will give you a hash value, and also we add what it is called the key prime, which is basically the remaining part of the key that we insert also in the leaf. It basically points out the level which the leaf is in until the bottom of the Merkle-Tree. Also, it is worth to mention that when we add the value of 256 bits, we split it in 32-bit chunks, and then here is the table. We split it in 8 different 32-bit chunks, and then it perfectly fits the input of the Poseidon. Okay, so we saw how to build a branch node, we saw how to build a leaf node, but what about the keys? Okay, which is the specification in order to build the keys? This is the specification. Which data do we know in order to differentiate the keys and in order to make sure that there isn't any collusion when you add a key value into the state tree? So first, we need to remember which are the fields that we need to insert into the state tree, which is basically the nonce, the balance, the code hash, and all the storage of a smart contract. So we need basically the storage position, the Ethereum address, and then we add this constant here in order to differentiate leaves. Okay? We will see in the following slide that this constant is going to vary in order to differentiate the keys. And, well, this is a little bit further explanation, but the output of the Poseidon, as I mentioned, is 4 field elements, and each field element is 63.99 bits. So you can see that the last bit is a little bit problematic. So in order to build the path from the key, we are taking the less significant bit of each field element consecutively. Okay, so we don't get the last bit, just in case. And this makes the path, the maximum length of the path, 252 bits. Okay, so let's see the specifics. Let's see which specific leaves we can find in the state tree. So the first one is the balance. As you can see, in order to build the key, we use 2 Poseidon hashes concatenated. And here, the first one, you remember in the specification that this input was about a storage position. So in order to insert the balance into the state tree, you don't need the storage position, so it's all set to zeros. Okay? And the output of the Poseidon is concatenated with the Ethereum address, and here it's important, the constant is 0. So the leaf balance, the constant is 0. Here it's important to mention that everything here in the first Poseidon is constant. So it means that we don't need to compute the first Poseidon hash because it's a constant. Okay, this slide is different. It's not the same. It's not the same one. But the only thing that changes is this one. This is how we differentiate from one leaf to the other. In that case, this is the nonce leaf. The value that we insert is the nonce, is 256 bits. And the third one, it's the code hash. Okay, so we insert the code hash, and again, in order to differentiate the key, then we set the constant to 2. But here it's also important that in Ethereum, when you perform the code hash, which is the hash of the bytecode of a smart contract. You just hash it. And here we are doing the same. We are hashing, but how? We are using Poseidon. We are using a chain of Poseidons with all the bytecode of the smart contract in order to get the code hash. And the last one, here we are using the storage position because the last leaf aims to store all the storage position of a smart contract. So we need to set the storage position in the first Poseidon, and then the constant is set to 3. Okay. In order to explain, to clarify a little bit, or maybe not, I'm going to put an example of how to add just 2 leaves into the state tree of the zkEVM. So here I'm adding a leaf of balance into the state tree, but how does it look like? Okay, so here we start from an empty tree, and then we insert one key value. And this key value is, the value is this one, the address is this one, we compute the key, and then we insert it into the state tree. So we will only have one node. And this node will be a final node, because we only have one. How do we know that? Okay, because we have the one. As I mentioned previously, there is a flag that points to you if it's a branch node or a final node. So, okay, now we know that we have a leaf node. So we can now interpret all the fields that we have there. The third fields elements are the remaining key. The second, fourth field elements are the hash of the value. So we need to go to an underlying database in order to extract the value from its hash. Okay, and the next one, a little bit scary. Don't worry. We add a second leaf in the state tree. So first of all, when we add the second leaf in the state tree, we need to we need to compare both paths of each leaf and then find the level in order to split them accordingly. So here, basically, 1, 2, 3 levels. We need 3 levels until finding the split bit. So here is the root, B878, which is this one. Okay, this node, it's a middle node or it's a final node? Okay, we have zeros, so the first 4 will be the left child, and the second ones will be the right one. So the left is empty. What about the right? 4398, 4398. Okay, it's a middle node. Left, right. Let's go to the right. D16E, D16E. Okay, here we have left and right, so let's go to the left. And the left, it's a final node, 571C, 571C. This is a final node because we have the one here in the capacity. This is the remaining key, and this is the final value. If you go to the underlying database, DA62, here you can read the value, which is basically 1. It means that is the leaf that we just inserted. What about the other one? 6603 is this one. You can read that it's a final leaf, and this is the value, which is basically the previous leaf that I showed in the previous slide. And in order to finish, which are the conclusions? This specification of the tree allows the viability of building the zkEVM, because otherwise it will waste a lot of resources and it takes a lot to compute. Also, we use the Poseidon hash in order to compute the Poseidon faster. We use the Goldilocks prime field number in order to accelerate computations. As you remember, in the keys slide, the maximum length of the path was 252 bits, and this basically makes that the maximum levels, if the Merkle-Tree are 252 bit levels. And also, we managed to store exactly the same data as Ethereum, since we want to be opcode equivalent with Ethereum. And that's pretty much. Thank you. Questions? Don't ask about the database.
Thanks for the awesome talk. I mean, this went way above my head, but still, I also missed the introduction, so maybe this is a stupid question. I mean, it's very likely going to be a stupid question.
I don't think so.
So you built this for zkEVM. Do you think that a similar tree structure is also possible to make proofs about the existing Ethereum structure? So, like, could you leverage this work to make proofs about existing state contracts? If you would retranslate the existing state tree into this tree? Well, I already see a nodding no, so I guess I got my answer.
You mean a transition from the Ethereum state to this state?
So yeah, if you would transition the existing Ethereum state into this tree, can you then make a proof that returns you the same root that you could easily verify against in a contract?
No, it's not possible.
Okay.
I mean, the hash function is different.
Yeah, right.
The specification of the structure is a little bit, well,
right.
a little bit, I would say.
Yeah.
It's quite different. So it's, I mean, the proofs will look like, and it will be totally different.
Okay, no worries. Thanks.
Thank you. You can ask me later, if you want. Okay, thank you very much.